In this lesson, we'll look at introducing differential equations. So our lesson overview is basically going to be defining what differential equations are. Specifically for us, we're looking at ODEs, and we'll explain that in a second. We'll then look at general solutions of ODEs versus particular solution ODEs. And then we'll look at a process to verify a solution to any differential equation. Okay, so to start with, we'll look at defining these differential equations. Now, what's important initially is to understand the scope of our syllabus. So in Queensland, the dot point that refers to solving differential equations is solve simple first order differential equations in the form dy dx is equal to f of x, dy dx is equal to g of y, and in the form f of x, g of y using separation of variables. So basically our syllabus sticks to a very small subset of differential equations, and that is that we're looking at separable first order ordinary differential equations. Now, just so you understand that the scope is quite large with differentials and we're focused on one particular subset, generally differential equations can be broken up into two forms. We've got partial differential equations and ordinary differential equations. So we're not going to look at partial differential equations at all, so we're going to ignore that. Ordinary differential equations can be broken up into further subsets. We're focused purely on separable and first order. So there's other types of ordinary differential equations we're not really going to cover, so I'm not going to talk about today. And obviously, first order, we're just looking at that first level of differential. So we're just looking at a dy dx, not a d squared y dx squared or anything along those lines. Okay? And then we're looking at these three specific forms of these separable ordinary differential equations. Our major focus will be on general solutions and then particular solutions of ordinary differential equations. So that being for any differential. Now, I should define that differential. A differential is any equation that involves a derivative function as part of its makeup. So that can be any of the following. Dy dx is equal to 2x. Here's an equation that involves a derivative function. It's therefore a differential equation. We could have a sum of x and dy dx is equal to 3. That would also be a differential equation. We could have second order differentials. We could say d squared y on dx squared plus 2 dy dx plus y is equal to 3. This is also going to be a differential. Now, every differential equation will have a general solution. Now, a general solution is just a function that fits the differential equation with unknown parameters. Now, if we use a little bit of extra information, then we can take that general solution and we can turn it into a specific solution. A nice easy example could be that we have the differential equation dy dx is equal to y. Now the general solution of this particular differential, and we'll learn how to do this later, would be that y is equal to ae to the power of x. Now, what makes this a general solution, not a specific solution, is the fact that we have this parameter a that is unknown. It could be any value. Now, so I guess that general solution represents a family of possible solutions where a is any real number, and any one of these possible solutions could be a specific solution based on that extra piece of information that is given. So, for example, we could say that when x is equal to 0, then y is equal to 3, and we could use that to work out that a is equal to 3, and therefore y is equal to 3e to the power of x, and what we end up with there is a specific solution based on that given data. So that may be true for a scenario that this original differential was intended to model. So that's what we're focused on today. Now, going back to this last dot point, where we're looking at focusing on verifying a solution to a differential equation today, to extend on what we've already looked at, to verify a solution, and that may be that we are looking at dy dx is equal to y, and we know that we've got a general solution of y is equal to 3e to the power of x, or we could even use ae to the power of x, it doesn't matter. If we're able to show that this is true for this scenario, then we can verify that. And so really it's just a left-hand equation, right-hand equation approach. We want to show that left-hand equation is equal to the right-hand equation. Alright, so if we focus first on the left-hand equation, we're looking at dy dx. Now dy dx will just be the derivative of 3e to the power of x. And we know in this case that will just be 3e to the power of x. The right-hand equation is just equal to 3e to the power of x. And therefore, we know that left-hand equation is equal to the right-hand equation. And so therefore we verified this general solution, or this specific solution, is true for this differential. Okay, so that's all the skills we're looking at today. We're not actually going to look at solving these differentials to a further lesson. So if we look at this first example, part A asks us to verify that y equals ae to the power of x take 1 is a solution of the differential equation dy dx is equal to x plus y. Okay, so let's look at putting this in. So what we'll need is we'll need to work out what dy dx is, and then we'll look at adding x plus y on that right-hand equation. So left-hand equation will be dy dx. Derivative of ae to the power of x is ae to the power of x. Derivative of negative x is negative 1. And derivative of negative 1 is 0. So that's done. That's our left-hand equation. Our right-hand equation, we're looking at x plus y. So we've got x plus, now y is ae to the power of x take 1. So plus x subtract x, and we're left with ae to the power of x take 1. Now what we can see here is that our left-hand equation is, in fact, equal to our right-hand equation, and therefore y is equal to ae to the power of x take 1 is a solution. Nice and easy. Now, hence find the particular solution of the differential given that y0 is equal to 3. So what we're saying is that when x is equal to 0, y is equal to 3, and we want to find the particular or the specific solution. So we know that 3 is equal to ae to the power of 0, take 0, take 1. So we've got 3 is equal to a take 1, and therefore a is equal to 4. And so that gives us the particular solution. Y is equal to 4e to the power of x take 1. Okay, nice and straightforward. Second example. This time we have a second order ordinary differential equation. So the only difference is that we've got this second derivative, we've got the first derivative, and we've got the original function, and the sum of all of these should equal 0. So before we start, we will need to work out dy dx. So dy dx will just be derivative of that. So we'll have derivative of 2x, which is 2 multiplied by e to the 2x. And the second derivative, d squared y on dx squared, will be the derivative of the derivative. So multiplied by 2 again, we've got 4e to the 2x. Now we can look at our left-hand equation. On our left-hand equation, we've got the second derivative, so that is 4e to the 2x. We've got the first derivative, which is 2e to the 2x, and we're subtracting 6 times the original function, which is e to the 2x. So we've got 4 plus 2, which gives us 6e to the 2x, subtract 6e to the 2x, and we've got 0. Now the right-hand equation is simply 0. So we have left-hand equation is equal to the right-hand equation, and that verifies that y is equal to e to the 2x is a solution. Again, nice and simple. We want to go one step further and show that y is equal to ae to the 2x plus be to the negative 3x is a solution of the differential equation. Again, it's the second derivative plus the first derivative, take away 6 times the original function is equal to 0. So we want to first find dy dx, and that will be 2ae to the 2x plus, well, it won't be plus, will it, because we're multiplying by negative 3. So it will be subtract 3b e to the negative 3x. And the second derivative will be multiplied by 2 again, and we've got 4ae to the 2x, and we've got plus 9be to the negative 3x. Now if we put this all in on our left-hand equation, we have 4ae to the 2x plus 9be to the negative 3x plus 2ae to the 2x, subtract 3be to the negative 3x, subtract 6 lots of the original, which is ae to the 2x, plus be to the negative 3x. Okay, so when we look at the a's, we've got 4ae to the 2x, plus 2ae to the 2x, and we're subtracting 6ae to the 2x. So that's pretty clear there. We've got none of those remaining. We have 9be to the negative 3x, subtract 3be to the negative 3x, and then subtract 6be to the negative 3x. And again, that's clear that that's going to be 0. So we end up here with 0. The right-hand equation is also 0, and therefore our left-hand equation equals the right-hand equation. And what does that do? That verifies that y is equal to ae to the 2x plus be to the negative 3x is a solution to our given differential equation. So we'll step forward to the last example, and it's a little bit different. It says find the constants a and b if y is equal to e to the 4x, 2x plus 1 is a solution of the differential equation. Second derivative, take a dy dx plus b y is equal to 0. Okay, so what we're looking at is to solve for a and b. In order to do that, first of all, we will have to find our first and second derivatives. So y dash, first derivative, this is going to be a product rule. So to find that, we'll first have to say that u is equal to e to the 4x, v is equal to 2x plus 1, u dash is equal to 4e to the 4x, and v dash is equal to 2. So what we've got is 4e to the 4x multiplied by 2x plus 1 and plus 2e to the 4x. Okay, so that gives us 8x e to the 4x plus 4e to the 4x plus 2e to the 4x, which simplifies down to 8x e to the 4x plus 6e to the 4x. Now we'll also need the second derivative. So we'll need the derivative of this one. So looking at y dash dash. Now this 8x e to the 4x will be a product as well. So we've got u is equal to 8x, v is equal to e to the 4x. Derivative is 8 and 4e to the 4x. So our second derivative will be 8e to the 4x plus 8x. Well, 8 times 4 is 32, so it's 32x e to the 4x. And we've also got the derivative of 6e to the 4x. So 4 by 6 is 24, e to the 4x. So it gives us 32e to the 4x plus 32x e to the 4x. Okay, so now we have to actually put this in. We've got our second derivative, which is, this is our left-hand equation, which is 32e to the 4x plus 32x e to the 4x. Subtract a multiplied by dy dx, which is 8x e to the 4x plus 6e to the 4x, plus b times the original, so that's b e to the 4x, 2x plus 1. Alright, so we probably want to group this into the x's and the non-x's. So with the x's, we've got 32x e to the 4x. We have negative 8a x e to the 4x, and we have 2bx e to the 4x. So there's all the terms with x's, and all the ones without x's will be 32e to the 4x, subtract 6a e to the 4x, and plus b e to the 4x. So that's our left-hand equation. Now the right-hand equation is 0. So each of these two things will be equal to 0. And that's what we're going to use to solve. So we have 32, take 8a plus 2b, x e to the 4x must be equal to 0. And over here we've got 32 take 6a plus b e to the 4x must be equal to 0. Now, this e to the 4x, divide out, it's 0. This x divide, it will be 0. So we end up with 32 take 8a plus 2b is equal to 0. And on this side, we end up with 32 take 6a plus b is equal to 0. So if we start by isolating b by going, we can say that b is equal to 6a take 32. We can say this is equation 2a. We can sub that into the first one, and we've got 32 subtract 8a plus 2 lots of 6a take 32 is equal to 0. Then we've got 32 subtract 8a plus 12a take 64 is equal to 0. So we've got negative 32, and we've got plus 4a is equal to 0. We end up with 4a is equal to 32, and therefore a is equal to 8. Once we know a, we'll be able to calculate b, so b is equal to 6 multiplied by 8 take 32. So 6 times 8 is 48. 48 take 32 will leave us with 16, so b is therefore equal to 16. Okay, so we end up with our coefficients a and b. So we take the same approach. But at the end, we've got a simultaneous process to find these unknown coefficients or parameters. Okay, so that concludes the lesson. Hopefully that all makes sense. Basically, what an ordinary differential equation is, specifically the separable ones that we'll be looking at. Remember, when we're actually solving differential equations, we'll mostly be looking at only first order differentials. Thank you.